Good afternoon, all. Welcome to the 47th lecture of Fluid Mechanics. We are in the Unit 3. So, today's topic is variation of friction factor for laminar flows and turbulent flows by using Reynolds number. Okay, by using Reynolds number, the variation of friction factor can be decided. Okay, so in the previous class, we have discussed about the problems related to the parallel pipes and also the power transmission in the pipe flow, their problems. Okay. So in this class, we'll discuss about the other topic, that is variation of friction factor with respect to the Reynolds number for laminar flows and turbulent flows. Okay. So we are on this point, that is a variation of friction factor with Reynolds number. So this is the topic we will discuss now. Okay. So the power transmission lines are already discussed in the last class. So how the head is checked at the center point. Here the pipe you are having with the uniform cross section. So the derivation, the efficiency, therefore the power transmission is capital H minus small h f by h. So the condition for maximum transmission of power and maximum efficiency of the transmission of power. So yesterday's class we have solved only few problems. So we'll complete these problems and we'll go to the topic. So problem 11.46. Consider a pipe length of 2000 meters is used for power transmission. If 110.362 kilowatts power is to be transmitted through the pipe in which water having a pressure, so water pressure is 490.5, as an inlet is flowing, find the diameter of the pipe and efficiency of the transmission if the pressure drop over the length of the pipe is 98.1 Newton per centimeter square. Take F is equals to 0.0600065. Here the power of the pipe is given, but we have to find the diameter. We have to find the diameter of the pipe and the efficiency of the transmission. Okay. Now taking the given data, what is the length of the pipe? Capital L is equals to 2000 meters. And what is the power transmission? P in kilowatts. Convert into power transmission. P is equals to 110.3625 kilowatts. Then what is the pressure having at the inlet? Pressure at the inlet P is equals to 490.5 Newton per centimeter square. That is equal to 490.5 into 10 to the power of 4 Newton per meter square. That is Newton per centimeter square. 10 to the power of 4 Newton per meter square. Then the pressure head at inlet. Therefore, the pressure head at inlet capital H is equals to P by capital P by rho G. Capital P by rho G is the pressure energy. Okay. The pressure already ichcharu kabatti input. We can take the pressure energy. Therefore, capital H is equal to rho by P by rho G. Then what is the P here? 490.5 into 10 to the power of 4. The given divided by 1000 into 9.81. That is equal to 500 meters. That is equal to 500 meters. Therefore, the pressure drop is equals to 9.81 Newton per 90. What is the pressure drop here? The pressure drop is 98 Newton per centimeter square. Converted to meter, 98.1 into 10 to the power of 1 Newton per meter square. Okay. Therefore, the loss of head. Therefore, the loss of head HF is equals to loss of head HF is equals to 98.1 pressure drop divided by rho G. Okay, 98.1 divided by rho G. That is equal to 98.1 into the power of 4 divided by 1000 into 9.81. That is equal to 100 meters. This is the loss of head. Then what is the coefficient of friction? 0.0065. Then what is the thing you have to find? The pressure head available at the end of the pipe. Right, the pressure head available at the end of the pipe is equals to H minus HF. So where ఈ ఫార్ములా ఎలా వచ్చింది? Here the end of the pipe H minus H, okay, H minus H F. So H minus HF is equals to the pressure head at inlet is 500, the pressure head at outlet is 100. So therefore 500 minus 100, 400 meters. Okay, now what is the thing you have to find? The diameter of the pipe. Therefore the diameter of the pipe is equal to small d. Okay, now the power transmitted is given by the power transmission formula, this one, right? Capital P is equals to rho into G into Q into H minus HF divided by 1000 divided by 1000. So this P you can see here, this one, okay. Power transmission P is equals to rho into G Q into H minus HF loss divided by 1000 into kilowatts. So applying power P value, rho 1000 value 9.81 into Q. So we have solved this one. The value is 400 divided by 1000. So after solving this one, so we'll get the Q value is equals to 0.02812, the discharge. But the discharge formula is equal to what? Area into velocity. Therefore, area is pi by 4 d square into capital V. Therefore, pi by 4 d square into capital V is equals to discharge value, this one. Therefore, then what is the V here? V is equals to 0.2812 into 4 divided by pi d square. Therefore, after deriving this one, we are getting this one, right? So what we have to find finally, we have to find the d value. Okay, now. Therefore, the friction loss HF is equals to the old formula 4 into F into L into V square by D into 2G. Okay, then what is HF here? The HF what we got is 100 meters. Therefore, substitute 100 meters here. Okay, substituting 100 meters. 100 is equals to 4 into F into LV square by D into 2G. So substituting F value, substituting L value, substituting. So we don't know the V value. So V divided by 2 into D into 2 into 9.81. Therefore, after substituting these values, we are getting this one. So 2.65 into D. Therefore, 0.3858 V is equals to 0.3858 by D square whole to the power of square, right? So that is equals to 0.003396 by D to the power of 5. Therefore, V from the equation V is equals to, from the equation 1, V is equals to 0.3858 D square. So that's why I substituted here from the equation 1 here. So we got V is equals to this value. So EV value ni, so they are substituted at this point, right? So they are substituted here. So therefore 100 is equals to 0.00336 divided by D to the power of 5. Therefore D is equals to, so D lost 100 lost. So 5 1 by 5. Therefore D is equals to, after solving this one, finally we are getting 127.7 mm. D is equals to 127 mm. Therefore, the efficiency of the power transmission is given by the formula efficiency is equals to H minus HF by H. So efficiency lost in the, so we have derived this from the maximum efficiency. Okay. Therefore, efficiency is equal to capital H minus HF by HF. Therefore, 500 minus 100 divided by 500, that is equal to 80%. Okay. So this efficiency we can calculate first only. Why? Because we know the value of H value and HF value. But according to the question, the diameter, find the diameter D and the efficiency and D. So we are deriving the efficiency here. Okay, understood the problem? So this is a way of doing the power type of problems. Okay. So Initially, you have to find the H value at inlet value, pressure of head, loss of head, HF value. After getting that, head available is capital H minus small h, that is into 500 minus 100, 400. The diameter of the pipe D. Once the diameter of pipe D is getting ready, then write the power P. So this is a formula for the power P. So after simplifying this all the values, you are getting Q is equals to this one. Therefore, Q is equals to area into distance velocity, that is equal to pi by 4 d square into V. So after getting this one, we are getting V is equals to 0.0358 by d square. So loss rate formula is this one. Therefore, we got HF value is 100. After getting HF value 100, so we know that HF value 100 into the formula. So after substituting the values in the formula, so we don't know the V value. So V value, మనం ముందు తీసుకున్న దాంట్లో we got the V value is this one. Now keeping this V value at this point, we are getting the value like this. So 100 is equals to 0.003396 divided by d to the power of 5. Therefore, D is equals to, substituting right side, so D is equals to 127.7. Therefore, the efficiency is equals to capital H minus small f by capital H. So 500 minus 100 by 500, that is 400 by 500, 0.80, that is 80% of the efficiency is used for the power transmission. So like this you have to do the problems whenever the power problems come in the exam. Okay. The next concept is variation to the friction factor. In case of laminar fully developed flow through pipes. In case of laminar fully developed flow through the pipes. In case of laminar fully developed through the pipes, the friction factor F, okay, the friction factor F is found from the exact solution of the Navier-Stokes equation. Okay, and it is given by F is equals to 64 divided by Reynolds number. So here we have to see variation of friction factor with respect to Reynolds number for laminar flow and turbulent flow. Therefore, the friction factor F is equals to 64 divided by Reynolds number. So in case of the turbulent flow, the friction factor depends on both the Reynolds number and the roughness of the pipe. Got it? In case of turbulent flow concept, the friction factor depends on both Reynolds number and the roughness of the pipe surface. Now, Sir Thomas Stanson started conducting experiments on the number of pipes of various diameters and materials. So, in order to check the variation of the friction factor, one of the scientists have conducted the experiments on the various pipe diameters and the material with various fluids flow. Later, a German engineer, Nirbus, carried out experiments of flows through the pipes in very wide range of Reynolds number. So by taking the concept of Reynolds number, RE less than 2000, more than 2000, right? So they have seen various experiments. We have done various experiments in a wide range by using the Reynolds number. So finally, a comprehensive documentation of the experimental and the theoretical investigations on the loss of friction in the pipes flow has been presented in the form of diagram. Finally, all this comprehensive documentation, what it has been experimented on the Reynolds number. So they made a diagram that is known as shown in the figure given by LF Moody. To show the variation of friction factor F. With the pertinent governing parameters, namely the Reynolds number of flow and the relative roughness of the pipe. This diagram is known as Moody's chart, which is employed till today as the best means of predicting the values of friction factor. So if you get any theory question, so define variation of friction factor with respect to Reynolds number అన్నప్పుడు, so you have to start this point, you have to write this point, right? You have to write this point, okay? Or explain Moody chart. లేదంటే what is the meaning? Define Moody chart means then you have to write a comprehensive documentation of the experimental and theoretical investigations on the laws of friction in the pipe flow, which has been presented in the form of diagram known as Moody chart. Right? The diagram given the parameters for the Reynolds number, the concept of predicting the values of F, the Moody's chart has been employed, and we can show in this way the Moody's chart, right? Okay. The next one is the friction factor F at the given Reynolds number in a turbulent region depends on relative roughness, defined as the ratio of average roughness to the diameter of the pipe rather than the absolute roughness. Okay, so whenever the friction factor with respect to the turbulent flow is given, it depends on what? It depends upon the relative roughness. Relative roughness defines the ratio of average roughness to the absolute roughness. Average roughness to the absolute roughness in case of turbulent region. In case of turbulent region. So next one. So whenever you are getting the moderate degrees of roughness, whenever the moderate degrees of roughness is getting, a pipe acts as a smooth pipe for a moderate degree of roughness. The pipe acts as a smooth pipe up to the value of Reynolds number, where the curve F versus RE, F versus RE for the pipe coincides with that of the smooth pipe. This zone is known as smooth zone on the flow. So if you see the figure here, so if you see the Moody's chart figure, friction factors for the pipes adapted in terms, right, in terms of values. So if you see the x-axis, you are having the x-axis, you are having the Reynolds number. The Reynolds number RE is equals to capital V into D by small v, right? That's the Reynolds number. So in the y-axis, we are having the friction factor F is equals to HF into D divided by V square into 2G into L. So keep in mind, whenever you ask a question, uh, uh, draw the Moody chart diagram. Explain briefly the Moody chart diagram. Just you have to draw a chart like this. Draw a rectangle figure, a box. On the x-axis, make it as a Reynolds number. On the y-axis, make it as a friction factor formula. Right? From here, make it as the numbers like this: 2357, 2357, 2357, 2357, 2357, 10 to the power of 3, 10 to the power of 4, 10 to the power of 5, 6, 7, 8 in the gaps. So in these gaps, okay. Maintain like this. Maintain the gaps like this. And 0 0.8, 0 0.10, 0 0.12, 16. So take the two, second table 8, 10, 12, 16, 20, 24 like that up to 70 to 80 up to 0.1. So just make the graph lines. So from center, from the corner point to the some extent, make it as a laminar flow. F is equals to 64 by RE. Okay. So from here to here, from here to here is a critical zone. Make it as arrow from here to here up to here. See here, from here to here, again from here to here, again from here to here, here to here. So it is a critical zone, it is a transition zone, and a complete turbulence roughness spikes. So keep these points in your mind. First critical laminar zone వస్తుంది, laminar flow వస్తుంది. First you will get a laminar flow, critical zone, transition zone, finally a complete turbulent zone, right? So from this one, see here, from here, from first point to up to here, it is a laminar flow. Next, from here to here, it is a critical region. From here to here, it is a transition flow. From here to here, it is a turbulent flow, that is roughness flow. Okay. So on the x-axis, keep Reynolds number. Y-axis, keep friction factor on the left-hand side. On the right-hand side, you keep the relative roughness, related roughness E by D. So just make a line like this. Critical zone నుంచి కిందకు ఒక line వేయండి. Just make a graphs showing like this. Show the graphs in this way. Show the graphs in this way. So what it is saying from this, from the moderate degree of roughness, a pipe acts as a smooth pipe to the value of Re, where the curve of F versus Re pipe coincides with the smooth pipe. This is known as smooth zone of flow. Okay, smooth zone of flow. Now, the region where F versus Re curves. See the region F versus Re curves. The friction factor F versus Re curves. See here, from here to this one. See the curves. Starting point, the laminar region tarvata, the critical region nunchi the curves are making the lines. So the region of where F versus Re curves become horizontal, showing that F is independent of Re. It is known as rough zone. Okay, see the figure. So whenever the curves are making, ఇక్కడ అదంతా కర్వ్ వచ్చింది. From here it is a straight line. From here it is a straight line. So this, see the variation. కట్ చేశారు కదా, this dotted lines తర్వాత వచ్చినవన్నీ, this dotted lines తర్వాత వచ్చినవన్నీ. So these are all the straight lines. These are all the straight lines. So these straight lines are called as the roughness pipes. Okay, the straight lines are known as the roughing zone, and the intermediate zone between the smooth zone and the rough zone is known as transition zone. Is known as transition zone. So smooth ki rough ki మధ్యలో ఉన్నది, smooth ki rough ki మధ్యలో ఉన్నది transition zone, right? The critical zone and the complete roughness zone. Smooth ki rough ki మధ్యలో ఉన్న zone is a transition zone. So the smooth zones, rough zones మధ్యలో ఉన్నది nothing but the transition zones. Means this, these are all the transition zones. ఈ కర్వ్ ఉన్నదంతా, these all the lines are smooth zones. The transition zones where it is lying in between the smooth flows and the rough flows, right, is known as transition zone. Next one. The position and extent of all these zones depends on relative roughness of the pipe. In the smooth zone of flow, the laminar sublayer becomes a thick, and hence it covers appreciably the irregular surface protrusions. Therefore, all the curves for smooth flow will coincide to each other. The position of the extent of all these zones depends on relative roughness of the pipe. In the smooth zone of the flow, the laminar sublayer becomes thick, and hence appreciably the irregular surface protrusions. Therefore, the curves for smooth flow coincide to each other. Next point. With increasing Reynolds number, the thickness of the sublayer decreases. So whenever the Reynolds number is increasing, with increasing the Reynolds number, the thickness of the sublayer will decrease. Okay, will decrease, and hence the surface bumps protrude through it. The surface will come out. The surface is like this. The surface, the sublayer, the thickness of the Reynolds number will protrude like this. Will protrude and it will follow the surface. The higher is the roughness of the pipe, the lower value of the Re, at which the curve of F versus Re branches off from the smooth curve. Next point. In the roughness zone of the flow, the rough zone of the flow means this one. This is the rough zone of the flow. The straight lines, horizontal lines are the rough zone of the pipe. rough zone of the pipe flow, the flow resistance is mainly due to what? From the drag of those protrusions. The pressure drop in this region is approximately proportional to the square of the average velocity of flow. Thus, F becomes the independent of the RE in this region. Therefore, at this point, what happens? The friction factor will be independent from the Reynolds number. The effect F is independent from in this region. Therefore, it is independent from the Reynolds number RE. So, if a question is given, draw a Moody chart and explain. First, draw the figure. First, draw the figure. Show the labeling Reynolds number at x-axis, y-axis the friction factor, right side you are having the relative roughness factor. Therefore, write the laminar flow first point, the laminar flow from at some point. Next point you are having critical zone. Next point you are having transition zone. Finally, you are having the roughness zone, right? So mark a graphs like this, starting laminar flow ending degree nunchi, make some graphs, 10 graphs like that, and just make a graph. But at some extent, you have to make all the lines parallel, horizontal it should be, okay? All the lines should be horizontal. But the distance we can change. See the distance here to here. So if the distance is కొంచెం తేడా ఉంది, distance is totally alike. You can maintain such type of distance, but the roughness line should be straight lines. ఇవన్నీ straight lines ఉండాలి, ఇవన్నీ curve lines లో కనబడాలి. And you can explain by seeing the figure, right? So based on this roughness factor, we will see some figures, some problems. Water at 15 degrees centigrade flowing through 200 meters long galvanized steel pipe. So the water medium is having some temperature, 15 degrees, flowing through 200 meters long pipe of diameter 250 mm, and at a velocity and at a volume, and at volume discharge, it is 0.225 meter cube per second. Note that the kinematic viscosity of the water is 15 degrees is equals to 1.14, and average surface roughness for galvanized steel is 0.15. So here what is given? New point is average surface roughness, average surface roughness. Steel is 0.15 mm. Then what is the thing you have to find? Loss of head due to friction, pumping power you have to find. So the first one is average flow velocity. Average flow velocity V is equals to Q by pi by 4d square normally. So Q is equals to V is equals to, what is the Q here? Q is 0.225. So meter cube per second, there is no need of changing the value unit. So Q is equals to 0.225 divided by pi by 4 into d square. What's the meaning of d square here? The d square is 250. Okay, 0.25 square. That is equal to 4.58. So we got the value of V. What is the Reynolds number RE? RE is equals to V into D divided by small v. Then what is the capital V? V is equals to 4.58 into D is equals to 0.25 divided by 1.14. What is 1.14? The viscosity, kinematic viscosity of the water, 1.14. That is equals to value is this one. So we got velocity V, average flow velocity, and the Reynolds number. And what is related to roughness here? The relative roughness is E by capital D, right? E by capital D. So what is capital D? 250. Capital D is equals to 250. Small d or capital D, right? Is equal to 250, and E is equals to point. What is E? The average roughness index, average roughness, surface roughness E is equals to 0.15. Therefore, roughness is equals to E by D and 0.15 by 250. That is equal to value this one. From this figure, from the figure 3.52, from the figure this Moody's chart. So C 3.52, see the 3.52, F is equals to 0.02, F is equals to 0.02, F is equals to 0.0, this one, F is equal to 0.02, at what? At roughness index 0.0006. ఈ 0.0006 దగ్గర F value వచ్చేసి 0.02. How you can see here 0.00005000040006. So ఈ value దగ్గర, so if you see the line making the line, so you are getting this 0.02, right? Or else they'll give, if the Moody chart diagram is not given, directly, they'll give the value. Take the value f is equal to 0.02. So after getting the value, so what is the formula you have to take? Hf is equals to f into L into d into v square by 2g. For circular pipes, dh is equals to d. Therefore, hf is equals to 0.2 friction factor f into 200 length by diameter into v square by 2g, v square by 2 into 9.81, that is equal to 17.11 hf. So the loss of head due to the friction hf is equals to 17.11. So ఈ hf తెలుసుకోవడానికి f we have to from the Moody chart, or it is given in assume, and we found the roughness, relative roughness value, right? And also we found the Reynolds number. So that is the answer for this average loss of head due to the friction. Next, B and D, pumping power required to maintain the above flow. What's the pumping power? Power formula. Therefore, the power is equals to rho into GHF into Q. That's equal to 1000 into 9.81 into 7.11 into 0.0225. What is the Q here? 0.0225. So 0.0225 minus, is equals to, so the value is 37.77 10 to the power of 3 watt, that is kilowatts. Therefore, P is equals to rho GHF into Q, that is equals to 10 to the power of 3 into 9.81 into 17.1111, that is equals to 37.77 kilowatts. So the power required for the value, the power required to maintain the flow of rate Q is given by P value, power is equals to rho into G into F. So taking this value into consideration, so we got the power is equals to 37.77. So this is a problem related to the friction factor roughness index. So when you get any question in the unit 3, average surface roughness అని ఇచ్చాడు అనుకోండి ప్రాబ్లం లోపల, then you have to straightly think about the friction factor formula, Moody's chart అని చెప్పేసి ఒక మీకు blindly you have to get the idea in your mind. That is, we have to use Moody's chart. That is our surface roughness index, E by D. Surface roughness, that is E by D. So you have to take the E by D. So E by D values తీసుకొని F values compare చేసుకొని, then you have to start doing the problems, right? So this is about the Moody's chart for the friction variation concept. Right? Hope you understood. So very simple of drawing the Moody's chart. Draw a rectangle, write the friction factor on the left hand side, write the relative roughness on the right hand side, write the Reynolds number at the bottom, and start doing. Write the 4 things: laminar flow, critical zone, transition zone, and the complete turbulence roughness zone. Then the friction loss, how the friction loss in the laminar flow take place, and how the friction loss in the turbulent flow takes place. Okay, so we'll see this one. The friction losses in the laminar flow. So because the laminar flow is so regular and orderly maintained, we can derive a relationship between the energy loss and the measurable parameters of the flow system. Okay, so the laminar flow is flowing in the pipe in a constant and regular flow. Therefore, the relationship is known as Hagen-Poiseuille's relation. So the laminar flows can be achieved by using Hagen-Poiseuille's equation, which we have already derived in the initial classes, and also the problems have been also discussed. Therefore, the laminar flow HL is equals to 32 mu into L into V by gamma d square. Gamma d square. The Hagen-Poiseuille's equation is valid only for the laminar flow. So already said that the laminar flow is only valid for Hagen-Poiseuille's equation. Turbulent flow is the Darcy-Weisbach equation. Okay. In summary, the energy loss due to the friction in the laminar flow can be calculated either by using Hagen-Poiseuille's equation or by Darcy-Weisbach equation. That is HF is equal to so and so. Darcy-Weisbach equation HF is equals to F into L into D, that is equal into V square by 2G HL. So that is about the laminar flows, the friction losses in the laminar flow. Next, the friction loss in the turbulent flow. Here the friction losses, the turbulent flow of fluids in the circular pipes is the most convenient way to use Darcy's equation to calculate what the energy loss due to the friction. So in the turbulent flow, we are using Darcy-Weisbach equation in order to solve the energy loss for the circle in the circular pipes only. Next point. The turbulent flow is a rather chaotic and is constantly varying. So turbulent flow generally the flow of fluid is not constant. The flow of fluid is not constant. It will be varying, and also it is a chaotic. Chaotic means it may be uncertainty. చెప్పలేం, the turbulent flow will have different uncertainty things. Next one. For these reasons, we must rely on experimental data to determine the value of F. For these reasons, we must rely on experimental data to determine the value of the F. The pipe wall roughness as the height of the peaks of the surface irregularities. This is not used. It's unnecessary point. Because of the roughness is somewhat irregular, the roughness inside the pipe is irregular. Averaging techniques are used to measure the overall roughness value. Okay, because the roughness value is somewhat irregular, averaging techniques is used to measure the overall roughness value. Next, for commercially available pipe and tubing, the design value of the average wall roughness has been determined. Okay, these are the only average values for a new clean pipe. Some variation should be expected. For example, if you take a laminar pipe, so if this is a pipe flow, the fluid is flowing. Inside you are having, if you exaggerate the inner surface of the pipes, with the inner surface of the pipe is having some irregularities like this, right? Some irregularities and it is flowing. So whenever the water is flowing in this direction, right? So the surface index, the peaks and the valleys, this gap. The average values of the new clean pipe. Some variation should be expected. After a pipe has been served in servicing for much time, the surface index could be changed due to the formation of the deposits. Okay, so whenever the pipe you are using for a long run in any application, what happens? The surface roughness అనేది. So the pipe, so you are having a pipe, లోపల surface roughness. So ఇక్కడ we are deposits are forming, salt deposits or some other chemicals deposits are forming on the pipe and attached. So దీనివల్ల ఏం జరుగుతుంది? Irregularities అనేవి form అవుతాయి, right? So after a pipe has been in service for a time, the roughness could change due to the formation of the deposits. అంతే కదా? The roughness of the pipe will change due to the formation of deposits on the wall of the pipe due to the corrosion. The surface roughness also takes change due to the deposits which are sticking to the pipe. So in that way also, the friction losses will be getting changed in the turbulent flow. Friction losses will be happening in the turbulent flow, right? These are all about the friction loss in the laminar flow and the friction loss in the turbulent flow. The friction losses uses Hagen-Poiseuille's formula. The turbulent flow uses Darcy-Weisbach equation. So like this, we have to see by using this chart. Okay. So in the next class, we'll discuss about the in details about the Moody chart, the applications of the Moody diagram, where you are using this Moody diagram. Okay. Next, we'll see the Eigen formula for water flow and also the pipe network problems. Right. Hope you understood the concept till here. So we'll discuss in the next class.